Hi everyone, my name is Michael Emmanuel, and I'll be teaching you gases and gas laws. And before we go into gases, we look at the states of matter, where matter exists in three well-known states: the solid, the liquid, and the gas state. In solid, the particles and atoms are packed very close to each other, and they don't have the freedom to move but vibrate in a fixed position, making it possible for them to have a fixed shape. Whereas in liquid, the particles and atoms are free to move around and take the shape of their containing vessel. In gases, the particles and atoms are free to move about. Their volume depends on the container that they are placed into. Now, other not so popular states of matter that doesn't exist in everyday life is the plasma, the Bose-Einstein condensate, which occurs in usually a very low temperature, below absolute zero, and neutron degenerate matter, which occurs in neutron stars. The plasmas occur when atoms are heated and the electrons escape the surface of that atom, giving rise to plasma. Gases are the simplest states of matter. They take the shape and volume of their container, and they are described using the following properties: the volume, the number of moles, the pressure, and the temperature of that gas. And it is specified by the equation of state, where the pressure is a function of the volume, the temperature, and the number of moles. If we know V, the volume, the temperature, and the number of moles of the gas, then P, the pressure, is fixed. And this is shown using the equation of state of a perfect gas. Now, take note of this perfect gas here, because we will be discussing the types of gas where we have the ideal gas and the perfect gas in the future. Now, the equation describes the relationship between the pressure and the volume and the temperature, the volume and the number of moles, the pressure versus the temperature, where R here is the gas constant with a value of 8.314. Now, Robert Boyle in 1662 came up with this relationship between the pressure of a gas and its volume. And it states that the pressure of a gas is inversely proportional to the volume of the gas, meaning that when the volume is increased, the pressure decreases, according to this equation here. Then Jacques Charles in 1780 came up with a relationship between the volume of a gas and the temperature, the pressure of a gas, and its temperature. Now, this relationship here states that the volume of a gas is directly proportional to its temperature, such that if we increase the temperature of a gas, the gas expands. That is, its volume increases. And on this side, it says that at a constant pressure and number of moles, the pressure of a gas is also directly proportional to its temperature. That is, as we increase the temperature and keep the volume constant, this is supposed to be volume. When we increase the temperature of the gas and keep the volume constant, the gas pressure increases. And this relationship is somewhat linear. That is, as the temperature is increasing, the pressure increases with almost the same magnitude. Now, the temperature here is the Kelvin's temperature, not the temperature in degrees Celsius. So if you face any problem that has to do with the temperature when it comes to these gases, you always have to convert the temperature from the temperature in degrees Celsius by adding 273.15 to get the temperature in Kelvin. Now, also, Avogadro developed a principle that shows that the volume of a gas is also directly proportional to the number of moles. That is, if we increase the number of moles, the volume of the gas also increases. Then we look at a few problems, and these include what would happen to a bicycle tire when allowed to stand in the sun for a long time? That is, if you keep the bicycle tire outside in the sun, the temperature of the sun increases and the temperature of the gases in the tires also increases. Now, as the temperature increases, the atoms and molecules begins to move around faster. Now, this increases the pressure in the tire. Now, since the tire cannot expand, that is, the volume of the tire is fixed. As the temperature keeps increasing, the tire will explode. So that is what happens when we place the bicycle tire filled with gases in the sun for a long time. Also, what will happen to an air-filled balloon placed in a refrigerator set at 0 degrees Celsius? Can someone tell me the answer? So this is basically the reverse of what is going on here. Now, when a balloon is filled with air and then placed in a refrigerator at 0 degrees Celsius, now, if the initial temperature of the gas is around room temperature and the temperature drops to 0 degrees Celsius, the gases begins to contract. Now here, the gases expand as the temperature increases. As temperature decreases, the gases begin to contract and become smaller. Hence, the volume of the gas or the size of the balloon will decrease, and the volume of the gas also decreases. Here we have a problem that says a spray can has a pressure of 1,330 torr at 25 degrees Celsius. What would the pressure be when the can is placed in a fire at 400 degrees Celsius? Now, this problem is showing us the application of the gas laws. Now, first, we look at the volume of the can is constant because there is no change in the can volume. It's fixed. Then we expect the pressure to increase as the temperature is increased from 25 to 400 degrees Celsius. And how did that go? How does that go? We have this relationship, okay, that the pressure of the gas varies directly as the temperature of that gas. And we have that the initial pressure is P1 and the initial temperature was T1. Then we also have the final pressure is P2 and the initial temperature, the final temperature is T2. That is, since this equation is equals to a constant and this is equals to a constant, then what we have is P1 all over T1 is equals to P2 all over T2. this is what we have here. So this equation can be rewritten to find P2. Now, if we substitute the values, P1 substituted by 1330, 1330 divide or multiply it by T2, which is basically 400 degrees Celsius per 273.15 Kelvin. Now, this will be 673.15. Then we divide it by the temperature T1, which is 25 plus 273.15. This gives us 298.15 Kelvin. Now this will give us the pressure 2. So we have a pressure P2. This value is 302.82. Now, do not forget to always convert your temperatures from degrees Celsius to Kelvin. Now, we will look at in the future the units of pressure. We'll look at the units of pressure, the units of temperature, and the units of volume. Once we understand how those units are derived, then solving problems in relation to gases will come very easy for us.